Now, how can you make intelligent social decisions? A policymaker must understand the current situation. You need to know what you're dealing with in order to be able to deal effectively with it. You need to be able to predict the result of any proposed changes in policy. And you need to evaluate the impact of these results on quality of life. So that's maybe a simple way of looking at it. You might be able to look at it some other way, but I just want to break it down this way. You need to understand, you need to be able to predict, and you need to be able to evaluate the impact on people's lives. So where does mathematical modeling come into this? Well, mathematical modeling provides a language for describing situations. You know, you have variables, you have equations, you have things like that. It's a very precise language. Maybe oversimplified sometimes, but at least it's precise. Okay? The method for analyzing situations, right? You look at different factors and you see how they affect each other, and you try to quantify that effect. Okay? All right. So as far as prediction, it gives you a way to assess strategies for changing or controlling. This is where the modeling comes in. You do your strategy. You try to express it in mathematical language, and then you can model it on the computer. And then evaluation is you have your quantifiable variables, and you try to see how different strategies will affect those variables, like income or crime rate or so on. And you want to know how your policies will affect these things. Okay, so characteristics of social mathematics. Sociology is concerned with the collective behavior of human beings. Okay? So individual human behavior, of course, is extremely complex. How can you model a person with a computer? It's just not possible. But however, when people get together, there's collective behavior. There's interactive behavior. And there's the joint behavior has statistical properties. You all know about the bell curve, the Gaussian curve, the normal curve, right? If you measure people's heights or measure people's weight or so on, individual heights and weights vary very much. But over the statistical region, you have some kind of regularity. So in this kind of social modeling, you want to focus on the statistical regularity. So social mathematics is essentially statistical. Okay? All right, so I talk about, now I think that for many, many years you have had descriptive models in social mathematics. You do statistics, right? You do measurements and you plot graphs and so on. You do demographics. You make projections and so on. Okay? So these are descriptive models. You have the classical statistical tools that, as engineers, I'm sure you also know, you have hypothesis testing, you have confidence intervals, you have some things like these. These are all common statistical tools. You use regression, right? And if you want to get tendencies and trends. This is you're describing what you see. You're not really explaining it, you're describing it, right? And this mathematical tools gives you a good way to describe these things. Like if you see a tendency and you continue the line, you say, well, if income is going like this, we expect it to be this next year, something like that. Okay? If the water shortage is going like this, you expect it to be this next year. You just can continue the trend because you can use these kind of mathematical fitting. So of course this is already a very important tool in determining social policy. Okay? And I think I just put in, as a mathematics person, I really want to put in a plug for this, is I think that if you really want to have a healthy government, people need to understand statistics. They really do, even just ordinary people, because, you know, politicians make promises that are impossible to keep. And you need to have some kind of understanding what these numbers mean. People just throw out numbers, and people don't know what they are. But I think that I really am a strong proponent of education in statistics. I think that's a very important subject that needs to be increased in the school curriculum. So, all right. Let's see. Oh, there we go. All right, now that's one kind of model. It's a descriptive model. You're describing things and using statistical language. Now there's another kind of model called a dynamical model. The dynamical model, it tries to explain what's going on. You have dynamical models in physics, right? You have F equals ma, right? You know that if you shoot the cannonball, you know where it's going to go because you have the equation that describes the behavior. Okay, so this is more behavioral. It's not just descriptive. You have an idea of the dynamics that is running the process. So you're able to predict the process. Okay? Okay. So dynamical models in sociology attempt to explain social phenomena in terms of forces and motivations. Okay? So you try to say the people are going to feel this way, how is this going to affect the overall view of society, and so on. Okay? So for example, in economics, you have this kind of model. Right? So economics is a kind of social behavior. And now, of course, there are many, many types of models in economics that people use. And they use Black-Scholes equation, they use some stochastic differential equations to try to model this. And this is a big business. There are thousands of people doing this, and they make money doing it. So in economics, you certainly have this kind of model. Okay, and certainly it requires expert knowledge, and it does have some built-in limitations. Often it's oversimplified. I don't know if you remember, but in US there was this big crash of the economy, and it was basically caused by people modeling. And they had oversimplified the model, and people were getting mortgages that weren't well-founded because people said the model says we can do this, but they oversimplified because everybody was assuming the same thing, and in the end people ran out of money and there was a problem. So there is a strong tendency to simplify too much. So you need to be careful about that. And usually you can only capture first-order effects. As I said, in life, in sociology, and economics, there's so many things going on. Usually you can only catch the very big, the very large effects. But you have to start somewhere. Okay? And I think you can only suggest and not dictate. You shouldn't take these models too seriously. You should take it as information, but not as the Bible. You have to say, well, we need to be careful about this. Okay, and the information tends to be qualitative and not quantitative. Often you can talk about tendencies or trends, but you can't give exact numbers, especially with the type of model I'm going to talk about. All right, so one type of social behavior is what I can call bursty social behavior, and this is really quite common. You have a video that goes viral on the internet. Right? Suddenly it has 10 million hits or something like that. How did this happen? How can you predict something like this? I don't know, but you can probably think of some video that everybody's watching, and you would never imagine, maybe some video of cats or something, I don't know, and you would never imagine that this video on YouTube would become so popular. But then somehow you have this small phenomenon that gathers and gathers. So you want to give some idea about how this type of phenomenon can happen. Another, as I said, I did some work for the Air Force, and of course they're not interested in cats, they're more interested in violence. Sorry. I can get some water. Sorry. So, give me a second. Maybe I should stop talking and ask if there's any questions.
Maybe we should give you a microphone.
I don't think that's the problem. It's not the volume, it's just something caught in my throat. And I like to use my hands. So. So as I said, there are other applications more serious than viral videos. There's things like violence. There are several recent examples. You have the Arab Spring, right? And it's very, if you think of how unpredictable that was, you could trace it back to in Tunisia. There was a man who burned himself, and then something happened. So these are actually, I think some of these are somewhat older. I'm sure you can think of more recent ones, but it seems that there's some small thing that happens, and then somehow it gathers momentum, and it becomes a huge movement. And this seems like something very difficult to model. I mean, If you talk about some mechanical model, you know, you apply a force on something and it moves a little bit. But it seems in this case, you maybe have some small event that has an enormous consequence. And that seems very, very difficult because mathematics usually is more continuous. You want to have some way of describing this kind of behavior and see if you can understand it better, what's going on. All right, so one way to model this is use this kind of method called agent-based. What agent-based means is that you actually can model every individual in the population. So you can see why this is very based on the computer, because you could never do this by hand. But in the computer, really, it's quite easy. If you know about programming, you can define an array, right? An array, you can define an array with a million, with size 1,000,000. It's not a problem. You can do that on a PC like this. And each entry in the array can represent a person. Now, of course, a person has many factors and complications, but you can do that kind of thing. So you also have these agents. So I'm talking about the individual people. I call those agents. So that's where the agent comes from. Now, agent can be a person. It can be something else. It could be sometimes in the internet, say. It could be a computer. It could be anything, any individual object or entity that interacts with other similar entities. So I call that an agent. Okay? The agents interact with each other. They're not just isolated. So people talk to each other. Computers or nodes in a network will interact with each other. So the interaction is what makes things interesting. And the interactions are individual, but they tend to follow certain regular patterns. So in this case, you need to use some kind of, you can't model exactly the interactions, but you can say more or less. You can give a probabilistic or statistical description of the interactions. You can make some kind of probability distribution to describe these interactions. And agent-based systems can be programmed on the computer. So I'll show you some computer code in a little while. So each agent will be represented as some kind of data structure. And interactions can be programmed. And typically some randomness is included to account for individuality. Right now, when I first started working on agent-based models, I said it was for the Air Force, and they were interested in violence. And the person who first started modeling violence with agents was a man named Joshua Epstein. And he came up with a very simple model, and he actually had a background in infectious disease. So you can see how this kind of agent-based model could be useful in modeling the spread of disease. Because, of course, if I have a cold and I interact with someone, they may get a cold, and then they go somewhere else and interact with someone and get a cold. So you have this kind of spreading behavior that results from the interaction of agents. Okay? So he thought, he had this background in disease, and he said, well, violence in some way behaves the same way. People see violence, and then they're influenced also to do violence. And it can spread in this way. So it doesn't need to necessarily to be planned, it can be spontaneous. So he would view a riot or a outburst of violence as the result of unplanned, spontaneous interaction of agents with their immediate neighbors. So in his model, he said, well, the people look around them and they see what the people around them are doing, and then they will behave according to the conditions that they see. So again, this is a very simple model, oversimplified model, but we're just trying to understand the basic way of thinking. Much too simple, but at least we can get some idea. Now, of course, you also have agents. You have another kind of agent, which he called cop agents. So you have agents who want to prevent the violence, so these are called cops. And so you have two kinds of agents. You have the agents, the population agents, and the cop agents. And the cop agents will if they see violence, they will try to suppress it. So if they see someone being violent, they'll arrest them. Okay? So the Epstein idea is that a person on the street, he will look around. If he sees 10 people being violent and no cops, then he has a strong incentive to be violent also. Okay? If he sees five people being violent and one cop, well, it's kind of iffy. If he sees 5 cops and 1 person being violent, then he's not going to do it. Right? So looking at the conditions around him, he reacts and acts accordingly. Okay, so this is what the model actually looks like. All right, whoops, sorry. All right, so I hope that this works. All right, so this is the model running. So you can watch it for a second and I'll explain what's going on. But you see the red coming up every once in a while. You see that red represents a burst of violence. Okay, so what's going on here is the blue dots are agents. This represents someone in the population. The black dots are cops. Okay. And the red dot represents a population agent who is acting violently. Okay. And the way that this is working is that the computer is computing for every agent. Every agent looks in his neighborhood. He looks to see if there's violent or non-violent. He looks to see if there's cops and there's not cops. And then there's a formula he uses to decide whether he goes violent or not. Now there's also a spontaneous probability of violence. So you can have someone starting out violent, so you might have some incident that produces violence. And then others around that person will either react or not react, depending on their idea. So if you watch again, all right, so you can see, all right, like you can see that when the violence comes up, it kind of propagates around or it spreads. Let me see if I can find it. Well, here you go. So you see that kind of wave of violence spreads there, and then it sort of dies out. So one thing you have here is you do have a mathematical model that does exhibit this behavior, where you have something small starting, and it can produce a large effect. And these large effects can be very irregular and have a very irregular distribution. So at least that mathematical model has that advantage, that it has this qualitative behavior that you see in civil violence. You do have this kind of behavior. All right, so this is the actual mathematical model. It says that. So this is the basic dynamics that the agent uses to decide whether to go violent or not. The agent may have a grievance, has some level of dissatisfaction. So that makes the agent more likely to become violent. The agent also has a risk aversion. He doesn't want to be arrested. Okay, so that if that's large, then he will be less likely to go violent. So you see that's a negative term. And then you have P, which is the agent's arrest probability. This depends on the agent looking around and seeing, well, are there too many cops? Or are there a lot of violent people so I can get away with being violent? So this one actually becomes the key, because this depends on the local condition. And what it says is that if the agent's grievance is large, and the probability that he will be arrested is small, then this quantity is large. Now, if it's large enough, if it's larger than a certain value, then that agent is more likely to become violent. So that's how it works. That's how it works. Okay. So let's see. All right. So for instance, all right. So here's the question: will this agent decide to go active? So this agent has a neighborhood that they look in. Okay. And here, and you can see in this neighborhood, there's 1, 2, 3, 4 actives, and then there's 1 cop. Right. So the way this works is that you take 4 actives plus himself divided by the cops. That's 5. Okay. So you have a scale. Right? The larger this ratio is, the more likely he is to go active. Okay? So I have this function which I can call activation function. I find 5 on the activation function. And then 5 goes up here, and then because not all agents have the same threshold, there's a distribution of thresholds. So according to this, in this particular population, it says, it looks like, I can't read it very well, I guess it's, let me see if I can read it on my screen. The 12, so I should have made it bigger. But this determines the proportion of agents who will actually go violent. So if this value is larger, right, then almost everyone will become violent. Right? If a person has the activation function down here, then they're very little likely to become violent. Okay, so you have this kind of nonlinear activation function which depends on the person's idea of the probability of being arrested. Okay? Now from this kind of activation function, we can get this kind of discontinuous behavior. Now just stop for a minute, and I do want you to think that this sort of thing may not just apply to populations, right? There may be other systems where you have this kind of behavior. Of course, if you have, say, if you have a power system, or you have a communication system, or any system that people are using, you may get this kind of behavior. People influenced by the people around them, and then your system might exhibit some kind of very discontinuous, very large change in usage patterns or so on. So I just want you to keep this in mind, that perhaps this way of thinking can be applied to something besides population. So and the agents would not be people, but maybe a mechanical system or physical system. All right. Now, this is a very, so what I showed you here was a lot of different agents. Okay? So, and you also saw in the video that I showed that you have large bursts of violence. Now, you can do statistics on those bursts of violence. You can measure how big they become, you can measure the time between them, and you can plot a distribution. So that's what this is showing here. What this is showing is the distribution of waiting times between bursts. So this is from Epstein's work, and he said set a certain level, and he said if the burst reaches this level, I'm going to measure it and record that as a violence burst. And then he measured the times between successive bursts, and he plotted the probability distribution. Okay. So you can see that, but there seems to be one particular time, preferred time between bursts, and then you have this kind of tailing off like this. So you may actually go a long time between bursts, but it's more likely that the bursts will be soon. So how do you explain this distribution? How do you explain this distribution of times between bursts? Well, if I'm looking now at the system at top level, I'm looking at the entire system. Okay? And I can say, if I look at the entire system, I can say, well, right now, there's an outburst, or I would actually characterize the system in 3 different ways. Either there's an outburst now, or it's recovering, or it's quiet. Okay? So let me just characterize the system in that way. Outburst, recovering, or quiet. And I have those 3 states here. Outburst, recovering, and quiet. And then I put something called a Markov chain. I don't know if you know about Markov chain. Do you teach Markov chains here?
Not me, but
we did. We use it in reliability systems.
Yes, I'm sure you do. So you have a system that changes states, and the system can change, has a probability of changing from one state to another. Okay. It's a very simple, you describe it using a matrix, right? A matrix of probabilities. So here I'm just setting up a very simple top-level description of my system, saying that the system is either outburst, recovery, or normal, then I assign some probabilities, and I can get exactly this same distribution just with this very simple model. So this is really telling me what's going on at a top level with this very detailed dynamics, that you can think of the system either as being in outburst state, recovery state, or normal state. And there's certain very random probability of moving from one to the other. Completely random and not something that is predictable. It's, I think maybe you might have, for instance, there's something called exponential distribution. Every time you turn on a light bulb, there's a probability that it will break, right? It's the same probability. Whether the light bulb is old or new, it's the same probability, almost the same probability. But then, and if you have light bulbs like this, and you plot the probability distribution of their lifetimes, you'll get something called exponential distribution. If the light bulb lasts 1 year, the probability that it lasts another year is the same as the beginning, okay? It doesn't matter. So that gives you exponential distribution. That's this kind of distribution here. So what this basically means is that there's no way to predict when an outburst is going to happen. You don't ever have any information that will help you to predict. Now, of course, the Air Force is not happy about this because they want to predict. But if that's what your model says, then you have to do what your model says. So, this type of model fits in a larger class of models called self-organized criticality. And if you're not a mathematician, you probably haven't heard of this. But but I can give you some. I think the first model of this is called the sand pile model. If you think of a pile of sand, right, and you slowly feed sand to the top of the pile, right, what's going to happen? The pile grows and grows and grows. What's going to happen? At some time, you're going to get a slide, a big slide, right? And then it may grow some more, and then another big slide, right? So this is also like an earthquake, right? What about earthquake? You have earthquake builds up pressure, 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 and then what happens? There's a big slip. I suppose you don't have earthquakes here, but you have these unpredictable large changes. You have a continuous process of building up pressure or building up sand or building up something. You have a continuous process, and then a big slip. And as I said, there are many models like this, and this has the same characteristics. Now, what happens in such models is you get some random instability. Something random happens that makes the system throw off equilibrium, and then that instability propagates outwards. And then once the instability propagates outwards, then the system relaxes. So think about the sand pile, right? If you pile up the sand, and then the sand starts to slide, after the sand has been sliding, then it stops, because you don't have the unequal distribution of sand anymore. So you have, the instability comes at some random time, it produces a large effect that propagates outward, and then it relaxes. So you're getting the same kind of effect here. For instance, so this is how you see it. You have some small group of activists, this just happens randomly. And they become violent here. So that's the first step. Then people in neighboring circles will see this, and they tend to become more violent. At the same time, cops see this also, and they move in here. But if the cops move in here, then they're not out here. Right? If they're not out here, then the people out here who are becoming violent, there are no cops there, so the violence propagates. It propagates outward. So the cops react, they go in, but the violence propagates outward. So this is the same kind of self-organized critical behavior. All right. Now, one thing about self-organized critical behavior is if you think about, there are some very general properties of the size of these outbursts. They tend to follow a certain distribution called power law. Power law means that here I'm plotting the logarithm of the number of events, and this is basically the logarithm of the size of events. So this is actual data. This is data. This is the data of riot events. This is all Africa, and then this is Nigeria. Okay, so I got someone who looked at newspapers, and this was during this period. And you know it's very, very hard to get this kind of data. So you have to be careful, but it gives some indication anyway. So what a power law would say is that the number of events, if you plot it this way, if you plot the logarithm of the size versus the logarithm of the number of events, you should get a decreasing line. So that's what a power law says. Now, there are other distributions like normal distribution, exponential distribution, which would predict something like this. So this here and this here, that's exponential distribution prediction. Now you can see that the power law fits much better than the exponential distribution. So there's some kind of indication that maybe this social behavior has some of these characteristics. Okay? Maybe we're on the right track. The model is much too simple, but maybe we're on the right track. Maybe we're getting something about what's really going on. All right. So this is a run. All right. So why don't I do this? I actually have some code here, and it's here. And where is it? I don't think I posted it. Oh, here we go. Okay. All right. So this is octave, and octave. Where's my? Right. I don't know how many of you have used MATLAB. Who here has used MATLAB? All right. Now, Octave is a free version of MATLAB, so you can download for free. And I prefer Octave to MATLAB because when I go to Nigeria or Cameroon, 99% of the copies are illegal copies of MATLAB. But Octave is free, so I prefer Octave. Now, the problem with Octave is the performance is much worse than MATLAB. Now, I'm sure you don't have pirated copies here. So everyone has a legal copy, I'm sure. Okay, so it may not be a problem. But just to let you know, if you're not aware of Octave, that is something you can download for free. If you just go to Octave download, you can find it. They have Windows version, Linux version, Mac version, so you can get it. And the way it works is very similar to MATLAB. In fact, you can take most MATLAB programs and run in Octave without any change. So this model here is an agent-based model. So you can see how I arranged it. Now this model here is a little bit different. It's kind of a toy model. When I was in Chad, during the night, sometimes the dogs would just start barking. It seemed for no reason. And then they would bark for some time, and then they would stop. And then maybe an hour, 2 hours pass, and then they start barking again. And then they kind of start, and I said, well, what's going on? So I thought, well, maybe I can model this, okay? So the model is that when the dog hears another dog barking, then he is inspired to bark also. You know, people have their houses and they have their dog in the courtyard. He hears another dog, he's inspired to bark also. So, but after he barks sometime, he'll get tired. So we'll stop barking, okay? So you get this kind of infection, the dogs influence other dogs to bark and then they get tired. So you get these bursts of barking and then you get periods when they stop barking. Okay? So anyway, I just thought for fun I tried to program this. So the code is organized like a usual code. You always have to initialize your variables. So these are my system parameters. And so this is I have to have a size of my neighborhood, the number of dogs. This is how far the dog can hear. This is so, and then I'm simulating for a certain amount of time. So these are all the parameters. Then here I have to do the probabilities. This is the tendency of the dog to bark, and then there's a mean and standard deviation. There's a normal distribution of the dog's tendency, and then there's a probability the dog will bark spontaneously. And then these are the interaction parameters that if the dog is barking for some time, he gets tired. This is kind of measure of his tiredness. And No, I'm sorry. If he stops barking, then he recovers from his tiredness. This is if he's barking and gets tired, and then this is the threshold beyond which he barks. So there's more details, but you can see that it's really, I just need to set some few parameters to describe the behavior of the dogs. Okay, so this is kind of like the size of the system, and then this determines the dog's behavior. Then I need to determine arrays. So as I said, when you have an agent, you need to put you have to put agent in an array structure. So this one here, each dog has an X location and a Y location. So that's what these two arrays are. And then at each time, the dog is either barking or not. So in this case, it's either 1 or 0. So this is another array that for each dog, it records whether they're barking or not. And then this gives me the entire record of the dogs barking over the entire period. All right. And then, all right, and then here, so here's my time loop. Should be able to go down. Now you can see it's not a very long code. This is it. This is the end of the code. So this is my time loop. So I need to do an update because at each time the dog's disposition is changing. Maybe because he's either been barking or not barking, so that changes his state. So I have to update his state. And then I have to decide then this one says some dog starts to bark spontaneously. So this one tells me when the dog barks spontaneously. Now notice that although this is a single statement, this is an array statement. So I'm actually updating all the dogs in one statement. And if you've done programming in MATLAB or you should always try to avoid loops because loops are very slow. It's much better to try to do statements that change the entire array at one time. So you can see I don't have so many loops. Many of these statements are array statements. And I think if I looked at this more carefully, I would even reduce the number of loops. So then this one here, you can see here that, now this is going dog by dog, and then this is basically, if you can see here, this is x squared plus y squared. So this is the distance. So you're looking at the distance from the dog to other dogs. Yeah, you have a question?
I say the time is.
Okay, it's running.
Yeah.
Okay.
All
Right. Okay. Sorry. Okay. So anyway, so here's the code, and let me just run it. Just run it right here. And the command window's here, and hopefully it doesn't take too long to run. All right. So it's running. I should probably go on while it's running because I don't know how long it takes to run. But it's going to produce, it will produce a graph. So let me go on with my presentation. All right, it's going to produce a graph something like this. This is showing graphs for 3 different levels of behavior. So these blue here are different outbursts. So you can see that this model does exhibit this outburst behavior. All right, so since the time is going, and I'm less than halfway through, let me skip very, very quickly. All right, so we did some studies on the system parameters and how they affect outburst frequency, outburst size, and so on. So this is just some details that I can pass through. So you can see that this kind of study can possibly help with policy decision. For instance, in the model, you can change the density of cups. You can say, well, how does that affect the level of outburst? Or you can try to affect the grievance. How does that affect the level of outburst? And so you can do these, and this is going to be a qualitative study, because how can you measure a level of grievance? It's not possible. You only have some qualitative idea. Right? So I said that I can just summarize this, that this model may give some generic insights. It gives you some idea, qualitative behavior of why the system is doing what it's doing. But it does not give you detailed information. And as I said, the Air Force was very disappointed. But what can I say? All right, now, sorry, so I'll skip over this. When I was there, I did a study of South African service protests. And I had no idea I would end up here, so I think it's just very appropriate. In this case, I guess you're familiar with service protests. So these are in Gauteng province. And In this case, the thing is that you don't just have local interaction, but because people hear things on the news, if you have a service protest over here, that may influence people over here. So you have to add something to your model. And I think that's one reason why you're starting to see more of these